climate change, renewable energy, nuclear power, water resources, and habitat, to name a few. Our mandate is to work towards a world in which all needs can be met in sustainable ways. We acknowledge that our work is carried out across treaties 2, 4, 5, 6, 8, and 10, and our office is on Treaty 6 territory, traditional lands of the Cree people and homeland of the Métis Nation. Tonight, I'm happy to introduce Phil Foster. Phil grew up in England, where he obtained his degree in combined engineering and a master's degree in electrical engineering. After working for 12 years in high tech in Europe and Canada, Phil decided to change careers and follow his interest in renewable and energy efficiency. For the last 17 years, Phil and his business partner, Brent Beach, have operated Rock Paper Sun. Phil has also continued his education and now has added journeyman plumber, gas fitter, HVAC designer, and energy auditor to his resume. Phil's business aims to integrate as many renewable and energy efficient solutions for customers with a focus on solar and efficient heating systems. Welcome, Phil.
Good evening, everyone. Can you hear me? So, my presentation this evening, I'm going to talk a little bit about renovations I've done to my own home. It's been basically a pilot project, testing ground for all the technologies, and then before I offer it to customers, I try to usually make the home first. So the picture you see in front of you is my house. And this is the year I moved into it in 2005, and at that time, the house was built in 2000. So normal November weather, yeah? So I'm going to talk a little bit about building envelope, solar thermal, heating, ventilation, and air conditioning, my natural gas heating system and ventilation system. Grid-tied, solar electric, photovoltaic, adding batteries to that system, electric vehicle, charging infrastructure, and hybrid cold climate heat pump. Thank you, Judy, for the introduction. So I think most things have been covered here. I also have I think the one thing that's on there is HRAI, which is the Heating and Refrigeration and Air Conditioning Institute. I'm certified as by them for the ventilation design and heat loss and gain for buildings. So talk a little bit more about that later. Some of the reasons why I'm doing this now is I was made redundant in 2007 from the high-tech company I was working for in Saskatoon. So it was kind of a, what do I want to do next? Almost 20 years later, still doing this. So a little bit about my home in Nutana. It was built in 2000. We moved in 2005. It's occupied by myself, my wife, mother-in-law, and our 2 teenage boys, one of which is now off in UBC. It's approximately 1,350 square feet on one level, with a basement below it as well. It's standard construction for 2000, 2x6, with an R20 bat in the wall. The HVAC system when we moved in was a really efficient furnace, builder basic, natural draft, water heater, 40 gallons, approximately 60% efficient, and it had a 10-seer, 2.5-ton air conditioner. From a ventilation perspective, it had regular bathroom fans and a whole home exhaust fan, which was operated in the kitchen. You could draw air from that, but there was no balanced ventilation. So the first thing I actually did, or one of the first things, was to think about the building itself, and building envelope upgrades are probably saving energy is one of the most important and one of the least expensive things you can do. And so the attic insulation was one of the things I topped up, probably added at least 10 inches to it to get a total of 26 inches, or around R60. The basement insulation, when it was built, a lot of new homes have insulation underneath the slab. In my case, there wasn't any insulation there. And so I added some internal insulation above the slab, which was rigid styrofoam. And it was part of an in-floor heat upgrade that I made. And I'll talk a little bit more about that. Air leakage, just regular things like replaced door seals and weather stripping, and sealed up leaking penetrations, and added some outlet gaskets. And so the air leakage is an interesting one. It's a huge proportion of a building's heat loss. And so if you can get someone to do a blower door test, you can identify some of those sources of leaks and try and fix them. Okay. Here's a little bit of what I did, basement insulation above slab. You can see that rigid insulation. Then there's a subfloor that's screwed down above that. And on top of that, in the right-hand picture, you can probably see some lines, and that's the in-floor hydronic tubing. A little square. Here is access for clean out for plumbing. An interesting thing that I wasn't expecting, because it's a relatively new build, is that my house has some issues with radon. I was fortunate to be at a presentation about radon, and a free test kit was available. So I put it in the home, followed the directions, and sent it off for analysis. And the results came back that the radon levels were higher than I was expecting. And so they provided more detailed data loggers over a longer period, and confirmed that the levels were enough that I needed to do some mitigation. And so the picture you see on the right here is a radon fan, and it's piped to the slab. There's a hole cut in the slab, and it depressurizes under the slab so that the radon can't come into the building. It gets exhausted, or less of it comes into the building. It's exhausted outside. I then added an indoor air quality monitor, which allowed me to see that drop in radon and confirmed that the reduction level is back to the safe levels that are recommended by the government. And so then the first thing we, as a business, and really what got us into the business, was looking at, we wanted to put solar thermal on our own homes. And so what solar thermal is a way of taking the heat that's coming from the sun, capturing it in a storage tank, and then using that heat primarily for heating domestic hot water. And so what happens is your existing tank, the water gets diverted around the solar storage tank, and then preheats that water, goes in back to your existing tank, and out preheated. And so it's quite amazing the amount of heat you can see off one of these systems. On a minus 30 degree day, I often see plus 40 degree Celsius temperatures coming off the panels on the roof. And my wife said, you should tell them when we were upgrading our heating system, we had 2 toddlers at the time who were in washable diapers, and we needed to be able to do laundry, and for a whole month we didn't have any other source of hot water. The regular water heater wasn't working. We just had solar and we didn't run out of hot water. It was in the summer, you're not going to get all the heat you need, but on an annual basis you're going to see 50 to 70%. Here's some pictures of the solar thermal panels on the roof. They're 8x4 glazed panels with a black back plate. And then you can see in the picture over here, this is the solar storage tank. This is the energy transfer station. It has a pump and there's some glycol solution that goes up to the panels on the roof here. And here was the original water heater with the bypass for the cold water now goes to the solar storage tank and the preheated water comes back. So it just passes through if there's enough heat. And if there isn't enough heat, then the regular water heater will top up the remainder. The system for those two panels is rated for around 8 gigajoules of offset of energy that would have had to be done by the, in my case, natural gas water heater. Next step was my HVAC upgrades. And so, as I said in one of the introductory slides, when I moved in, it was a very basic furnace and water heater. There were 80% for the furnace and 60% efficient. So I wanted to upgrade that heating and hot water equipment. So at the time, there was Saskatchewan grants for energy improvements as well as federal grants. And there was a new product that was just introduced into the market called an integrated mechanical system. And it's basically one box that can do multiple things. So it had the ability to do forced air space heating, domestic water heating, ventilation with heat recovery, and hydronic heating, all based around a natural gas boiler that was around 93% efficient. So an upgrade for both the space heating and my water heating. And my wife complained of a cold basement. Little did she know what the plan was in my head. Coming from Europe, I was used to boiler heat and hydronic heat, and so now, after many years of renovating, we have in-floor throughout the house, and I love the warm floors, especially in the bathrooms. So here's a picture on the right. Of the integrated mechanical system. In the top half here is a boiler, below it, the bottom half is HRV, and then coming off the side there's indirect connection for domestic hot water, and then I have loops with manifold actuators here for the inflow. A little bit more pictures. So on the left-hand side, this is a basement bathroom. You can see the tubing in the floor, which is going to have a floor leveling compound added over the top and then tile above it. In the middle is a towel warmer that's heated from that same system. And then for areas where I had hardwood flooring that I didn't want to remove, I put below that floor these aluminum plates with tubing between them, and then below that a layer of insulation to stop or try and minimize the amount of heat that would migrate down and try and force the heat up. Some of the other measures that were smaller measures in general. When we moved in, we had no appliances, so we left the appliances at the previous building we were living at, and so we bought new appliances. European style appliances, typically smaller, more energy efficient, saving more water. I upgraded the toilets to be low flush style toilets, faucets and shower heads and aerators with lower flow rates, added rain barrels to the garden, and then the electricity so then a few years later, so we started the solar thermal around 2007, 2009, 2010. We started to do our first solar electric or photovoltaic systems. And for those of you that don't know how this works, it's a pretty straightforward process. You have a solar panel on the roof that produces DC direct current electricity, kind of like a battery. And then the electricity we need in our homes is AC electricity, 240 volts. And so the systems we've been installing have what's called a microinverter, and those are mounted behind the panel. And they take that 30 volts approximately of DC electricity and can invert it to 240 volts AC, which is compatible with your house. And so that electricity gets tied into your electrical panel. And so if your home is, or your solar is generating energy, it gets used in your home first to power the loads inside your home. And if there's any surplus energy, what happens to that energy is it flows backwards through your meter back onto the grid, and your neighbours get to use it. There is a register on that meter to tell the utility what you have fed back. And I'll talk a little bit more about those credits later. One thing to note with grid-tied solar, 95% of the inverter systems out there say that when the utility grid is not present, solar cannot generate power either. Which means that although you've got this solar and there's a bad winter storm comes through, you don't get any energy out of the solar at that time. We're very fortunate here in the city, Saskatoon Line Power, their reliability is pretty high, as well as SaskPower customers. The more remote you are in the province, I don't know how reliable the grid is. It's pretty good. So I'm going to just talk through being in the business. You get to play with technology through the years, and so back in 2010, when I first put on solar electric panels, I added 12 185 watt panels for a whole big system size of 2.2 kilowatts. And the cost at that time was around $8,000 a kilowatt. So a very large expense. We had a few panels left over from another project, 3 in fact, so I added those on in 2011 just to increase the size a little bit. Then by 2012, I decided that you can see the size of panels went up quite a lot in what was available, 250 watt panels now, and I added another 10. And then again, by the time we got to 2020, when I also added batteries to the system, the size of the panels had gone up another level to 325 watt approximately. And so over the years, I've accumulated 15 kilowatts of panels and a total of 55 panels of varying size. By the time we were done in 2020, the costs were around $2,500 per kilowatt. As you can see, the price dropped a lot. The next few slides just show a little bit of detail of those phases. So 2010, we've just got the smaller panels surrounding my solar thermal. Solar thermal on the model 8 here. There's 2 on this side, and there's east-west facing roof here. This is south facing. I did a little bit of rearranging. As you can see, there's a little bit of shade on the roof. It's a mature tree neighborhood, and so solar thermal is less susceptible to shade, whereas solar PV is more susceptible to shade. So I relocated those in combination with I needed to replace And so everything came off, rearranged things, and now I don't have any on the east roof. We just have 3 on the west, and the rest are on the south facing roof. And then in 2012, I built myself a workshop, the building on the right. This pitch of this roof is 60 degrees, and the north-facing roof here is 30 degrees. I wanted to try, based on some experience with other projects, a steeper sloped roof, and how that would work with shedding snow. On the garage, you'll see there's 2 panels on the south-facing wall, and those are adjustable. I wanted to try and get some data at different angles, so I added an adjustable rack onto the end wall. And then in 2020, I put panels on the east-west face of the garage roof and rearranged the bigger panels, the newer panels, to be the south-facing ones. You might just see there's 2 panels here on the north-facing roof as well, just because I wanted to know what the data was going to be like for those and how they would perform as well. And to answer that question maybe in advance, they're about 50% of the output of the south-facing panels, but not 0. This is what a microinverter looks like. It's attached to an aluminum rail. The aluminum rail has flashings on the roof, which are attached to, and then the panels go on top of these rails and get clamped down with hardware to those rails as well. Okay, so batteries with grid-tied solar. This was the next step. So batteries are charged by surplus solar energy. When they're fully charged, the excess power is fed back to the grid as it would have been without the batteries. When the home is using more power than solar can provide, it takes from the batteries until a minimum threshold is reached. The batteries are lithium iron phosphate, there's 0 maintenance, and they're warranted for 15 years. This is an output from the monitoring system, and you can see here the blue part of the chart is the solar production. The orange is my consumption within the home, and the green is the charging of the battery. So if you look at this is the state of charge of the battery, and as the solar comes in here, the battery starts to charge until it's full, and then I can start to discharge it when the sun goes down and use that energy later. So the system I have has multiple modes of operation. You can have full backup mode, which allows the system to back up loads in the event of an outage. And you can dynamically change this from an app on your phone whenever you want to. There's a self-consumption mode, which allows surplus solar production to be stored locally and used later. It might be a good model for SaskPower customers under newer net metering program agreements. And the final mode of operation is a time of use one. It's targeted more at utilities that have time of use differences in their power rates, but it allows stored power to be used when electricity rates are highest. I believe SaskPower will at some point go to this time of use rate, so it would be a useful thing for most customers in that regard. Some modes you can decide if you want to charge from the grid or from solar or a combination of both. You can also set thresholds for reserve capacity. I keep mine around 30%. Unless I know there's a storm coming, and then I can set it to be fully charged, ready for that storm. So a little bit about the batteries. The picture on the right is one single battery, about 3.3 kilowatt hours of capacity. And in 2020, I added 4 of those batteries, so the 13.3. They were selling off this generation of battery in 2025 earlier in the year, so I added an additional 10 kilowatts at a reduced price. So I now have 23.3 kilowatt hours of capacity. It can power a continuous output of 8.9 kilowatts, with a peak output of about 13.3 for those surge loads, motors starting, inductive loads, etc. And my mode of operation is self-consumption, so I'm really using it to be a better solar person from the utilities perspective. They see less of my power going back to the grid. But the side effect really is that I also want to have resiliency if we do get storms or more severe weather. And I've had, I think now 3 power outages, and I haven't noticed them. My neighbours go black and I just carry on. It's kind of interesting. You get a message on your grid that the grid's out. Oh, okay. All of it's controllable by an app, the load management, the mode thresholds, etc. This is what it looks like in my garage now. Thanks to Brent with all his hard work of doing all the wiring in this. It's whole home backup, so it's not just a subset of the loads. However, when I do go off grid, I drop some of those loads. My heat pump drops out and my EV charging drops out. Again, I can turn some of it back on dynamically as well if I want to. Inside the box in the middle is what's called a microgrid interconnect device. It's what people might have heard of it as like a transfer switch. It's the ability to disconnect from the grid. So the utility requires you to be disconnected from the grid in the event of an outage if you still continue to use power. And that's the part that does that. And then on the walls also some inside here is all the controls, and these are the batteries. There's 1 battery inside of here, and 3 batteries here. Surplus energy. So the utility allows you to carry forward credits. So there's a couple. The 2 utilities I know about are Saskatoon Power, which is who powers my home, and you can carry your credits forward for a year and then they're reset in April. Sask Power, if you had a system that was installed before 2019, then their credit actually only expires every 3 years if you have surplus. And new customers, the credits don't expire at all. However, if you're a Sask Power customer, they've changed their scheme so that the credits that you give bank, you have to buy back from them at a 50% of their retail rate. Saskatoon Power still has the full value for their credits, so we're very thankful for that. After I expanded my system to the 15 kilowatts, I had surplus credits at the end of the year, and in fact in spring of 2022 I gave the utility almost 3,700 kilowatt hours, approximately $580 in value. So I thought, that's not a good plan. I'm going to find some uses for that electricity. And so you can see here the blue line on the 2022 chart. Our blue line is the solar that I'm generating. The red line is the energy that I'm asking from the utility. And the total consumed is the yellow line, And then the carryover is the green line. As you can see, because the utility reset my balance to 0, I get that steep drop in the green line there. And so by 2025, I'd fixed that. I'd used up my energy before they took it away from me. And this is how I did it. I added an electric vehicle. Had to wait. It was kind of during COVID times, just coming out of it. Everything was slow. They had production issues, callbacks and things like that. But anyway, I ended up with a vehicle. I'm very happy with it. It approximately reduced that surplus by another 20%, down from the 35% I had. The service upgrades I made to add batteries, etc., made it easy to add the charging infrastructure in the garage. Recently, I've added a smart EV charger. So the manufacturer of the inverters and batteries produced an integrated smart charger. And what that does, it allows me to say to the charger, I only want to charge my vehicle when there's surplus solar energy or surplus stored in my batteries, if I don't care about how fast the vehicle charges. So I can plug it in on a weekend and recharge it slowly, because it will vary the rate of charge depending on what is being produced by the solar panels. But I optionally can also charge it at full speed rate as well. And I have the ability to do that directly when I plug in time or through the app. And if you look at the app here, you might be able to see that this was the solar generating at the time. This was live, and then 1.2 kilowatts going to my batteries on the wall of my building, and then the remainder was going to feed my house and then to charge my vehicle as well, and a little bit was flowing back to the grid as well. And then we had another vehicle that was a hybrid that we wanted to replace as well. And so my youngest son competes in speed skating events in Calgary. And so driving on a pure battery electric vehicle was pretty hard to do on that route to Calgary. The infrastructure to recharge and the spacing was hard, so we decided we still needed some form of internal combustion engine. So we went with a plug-in hybrid vehicle, and that's what we chose. It does 95% of its time in and around the city, and so we use the solar to charge it and run around the city. But when we go on long-range trips, we can still use gasoline. There's a few details about the vehicle there. Okay, and then the final thing I'm going to talk about this evening that I've added is air source heat pump. And so I wanted to talk a little bit about what heat pumps are and how they work. And so this picture on the right is a little bit of detail, but I think the important thing to note is a heat pump doesn't produce heat, it just moves heat. So it takes that low-grade outdoor temperature heat through a compressor, it increases that low-grade heat to higher temperature heat and moves that, and then that heat is then given up inside your building, and then the cycle repeats. The physics of it, and you go from low pressure to high pressure, low temperature to high temperature. It's just the same as a regular air conditioner, except it's working in reverse. If you think about your refrigerator in your home, it's it's doing the same thing. It's removing heat from inside the fridge. It's not adding cold, it's removing heat. Anyway, that heat pumps have been around for a long time. The difference is now there are what's called cold climate heat pumps, and they have the ability to work out temperatures below -5 Celsius outside, and as low as -30 Celsius. So in that climate, as you're well aware, we get below -30. So we can't just use a heat pump on its own, and we need a backup of second stage heat. In my case, I reused the existing boiler air handler, which uses natural gas for that. But you can have electric resistance heat as the backup as well, but you will need a second form of heat. When it's running, the heat pump runs first to the selected changeover outdoor temperature that you set when you want that to change over. And I'll talk a little bit more about picking that number in a second. So a little bit of detail about the specific equipment that I installed. It was added in 2024, and as I said, I replaced a 24-year-old air conditioner that was only 10 SEER with a 3-ton GREE outdoor unit, and added a new indoor coil, line set and wiring. The new unit in cooling mode is a 17 SEER. SEER 2 is the new standard, and then this HSPF is its heating rating, and it has a performance of 9 in that category. Coefficient of performance shows how much you're getting out of the system for every unit of energy you put in. With an outdoor temperature of 8 degrees C, you get 4 units of energy out. When the temperature drops to -15, you only get 1.8 times the energy out. System will work down to -30. It has a quiet horizontal discharge fan on the outdoor unit. It has an inverter compressor, variable speed that can ramp up or down to meet different loads. This is what it looks like on the outdoor. This is what I mean by a horizontal fan. Most people's air conditioners have a fan on the top and they blow vertically. This one blows horizontally. It's very quiet. The fan is molded fiberglass, and it's almost like an airplane blade. It's very quiet. Indoors, you have an air conditioning coil just like you did before, except they're a little bit more dense and they're taller to get those efficiency ratings. One thing I wanted to mention is that because these are now running in the wintertime, you need to put them off the ground, so you can mount them. In this case, it's mounted on the wall about 2 feet off the ground. You can get a stand as well that you can put them on. The reason for this is they go into what's called a defrost cycle, and they defrost the coils, and they produce condensate, and that condensate needs to run away. If it sits in the bottom of the unit, it would freeze up, and then the unit wouldn't work. So if you're getting somebody to install this, make sure they know what they're doing. There's been a number that have been installed on the ground and had problems. It has inside the base of this inside the base it has a heater that comes on to keep that condensate as liquid as you can imagine. It would freeze at the outdoor temperatures, but it keeps it liquid until it leaves the unit. Other things you should be aware of is that you may need to do more maintenance during the winter, because if you have a snowstorm or a blizzard, this thing still needs to work. And so, you need to make sure that snow isn't getting stuck in the fan, stopping it from turning. In fact, this is underneath an eave, but the eave's quite high up, So I did have to clear out snow one winter to get it to continue to work. Something to be aware of. Okay, some people may know about balance point, but I'm just going to go very briefly through this. What I've done is I've plotted on this chart the heat loss from my building, which is the red line. As you can see, at 21 degrees Celsius, there is no heat loss because that's the same temperature as the inside of the building. When it's minus 30 outside, I have around 35,000 BTUs an hour leaving the building. And so I have to replace those with the heating system. Now, the heat pump has different efficiencies, COP, at different temperatures. And so I took the data from the manufacturer and plotted that blue line. So it can't produce heat below minus 30, so that's why the line drops off at minus 30. But as you can see, if I want to heat my home at minus 30, my heat pump won't put out the temperature I need, which is here, at minus 30. So this point here is called the balance point. This is when my heat pump will match the load of my building. So everything to the right of here, my heat pump can now do, but everything to the left of here, it can't keep up. And so you could get around that by installing a larger heat pump, and then that will move your curve higher up this. But you end up with more cost and an oversized system potentially, and you've got to have backup heat at some point anyway. So in my case, I could run this down to about minus 18, and my building would still be comfortable. In reality, I don't run it quite as low as that. I run it to minus 5, minus 10, and I'm playing with those numbers and learning a little bit. So you can set that changeover temperature in your thermostat. Okay, I'm the engineer, so there's another graph. So what I've done here is I've tried to quantify what the cost difference is between electricity running a heat pump and if you were doing the same thing with natural gas. Now, people might not be aware that natural gas per unit energy is currently, in our province at least, 7 times less cost than that of the electricity. So when I take into account the fact of maybe a 93% efficient boiler, that drops to only a 6.7 time difference. And then the COP of the heat pump helps, but even then gas is still 3 times or less cost than it would be if you were heating with natural gas. So in my case, it's not a problem because I'm using that solar-free energy that I've banked, so I'm not paying these costs. But if you were getting the energy directly from the utility, you are going to pay more. So you need to make the decision whether it's worth it for you to pay that additional money to offset the carbon. And then you need to think about what the utility is doing to generate their electricity and how clean that electricity is. So there's arguments that the natural gas that you might burn in your own furnace or boiler is actually cleaner than getting electricity generated from a coal-fired power station, for instance. But Saskatoon region has natural gas-fired power station at the Queen Elizabeth, and we're adding more solar and other renewables into the local mix. So I don't know what proportion of our electricity comes from outside of the Saskatoon region. So I can't answer that question. It's a question for Saskatoon. Moving back to the chart, you can see I've added the COP into the costs here. So the more energy efficient as it gets closer to the 20-degree temperature, then the difference between the costs is less. But the colder you go, the more the cost difference is between natural gas and electricity to run the heat pump, if you were choosing between the two. Hopefully that makes sense. The last thing I've had installed in the last month, I've installed for a number of other customers. I got involved with a green box pilot program. What this little box does is it wires into your heat pump. It's a hybrid heat pump system, so there is a backup. And in this case, they all wanted to be natural gas backup. And what it does is it gives you the ability, although the thermostat is saying I want to use the heat pump right now, it can say, no, I'm actually going to use natural gas instead, based on a control. And you can make that trade-off analysis. You say, well, okay, I want it to be lower cost right now, or I want to reduce my carbon footprint. It gives you the ability to easily change that changeover temperature or lockout temperature. And I'm working with the team, they're based out of Ontario, to try and improve their design a little bit to take into consideration solar customers that have solar in combination with heat pumps. In my case, I'd like to be able to use my solar credits, so be able to see those being used up and then stop potentially using the heat pump until the spring and I have more credits again. But also the ability to only use the heat pump when solar is generating and maybe when there's surplus power as well. So those are some additions that they're hoping to add for me. This is the interface as it stands. They're still developing it, so it's not fully online yet. If you look at the slider here, it gives you the ability to look at last month's data and make a what-if analysis. What happens if I slide the scale to the left? I'm going to lower the cost. I'm going to use the gas more, and how much would I save? If I slide the slider to the right, I'm going to get lower emissions, but it's going to cost me more. And then this chart kind of shows, this is real data from my own home, when my furnace has been running and when my heat pump has been running, and then there will be green bars on there when the green box has changed what the default would have been to run natural gas instead. So you can see my set point right now is -5 Celsius. My heat pump is running, it's been fairly mild in November, so it's running quite a bit, and then on the colder days, the furnace the boiler will take over. So again, engineering, we like to measure things, and so data measurement, by observing what we're consuming, we're more likely to change. And so the solar and a number of other monitoring systems in my home allow me to look at what I'm using, what I'm generating. And you can do that even by looking at billing. My wife for a number of years has been doing that. In fact, these next two charts show some of that data. So we look at how we're doing each month in terms of water and electricity. You can see anomalies. We identified an anomaly back in 2020. You had a leaking toilet that wasn't visible that it was leaking, but it was using a large amount of water. Just by looking at your bills, you can find this sort of information in. So how is my home rate after all of these improvements? Well, if you look on the left here, this is my latest Energuide audit. They come and do a blower door test and look at the equipment you've installed. And so with my renewables, that's the solar electricity, and my solar thermal, I use 13 gigajoules in a year after those offsets. A typical home would be about 120 others. So if you're picking or sizing equipment, solar side of things, what we tend to do is look at the existing annual load from your utility bills in kilowatt hours, and then we look at the available space that you have on your property, be it on roof or on the ground, the direction and pitch of roofs, what you might want to do in the future loads, EVs, heat pumps, etc. My recommendation is go as big as you can, because you will always find uses for that electricity. Batteries. So how much do you want to back up? Go through an equipment list, see which things are important to you, and how long an outage are you willing to suffer. So the cost increases with the longer the duration you want to be off the grid. Heat pump sizing. Talk to an installer or a designer. Look for the most efficient equipment you can afford. There's an Energy Star Best equipment. Look at the ratings, inverter compressor, right size the equipment. I can't emphasize this more. Don't just go for the biggest thing you can find. It doesn't work well. Get a proper heat loss on a renovation, because most people's homes have improved from when they were built, and the equipment that was put in when they were built might have been in the back of an envelope. Get a proper heat loss analysis, see what your building should be sized with. You're going to need controls. Most modern thermostats will have the ability to run heat pumps and allow you to control that changeover point between when your backup heat and the heat pump is running. If you are replacing both pieces of equipment, not just adding the heat pump and reusing the existing heating equipment for the backup, then I would recommend using the same manufacturer for both of those equipment. You get a little bit more efficiency because those two pieces of equipment can talk a little better to each other and get the units to ramp up and down in more sync. They all work better. Something about the costs of equipment. As I mentioned earlier, my $8,000 a kilowatt back in 2007, those costs have come down about 85% in those 18 years. We're now at around 2,500 to 3,500 per kilowatt installed, and it really depends on the size of the system. The smaller the system, it's a little bit higher. The larger the system, there's still a certain amount of infrastructure that's required, regardless of the size of system, that kind of factors into that. The average systems we've been installing typically are in the 6 kilowatt range, around that $15,000 mark. Battery systems will almost double, if you add a battery to the system, almost certainly double the cost of the system or more. It's not a cheap option, but it depends how important it is to you to have that backup energy, that resiliency, and or other uses for it. Hybrid heat pumps, they're custom sized around the building requirements, so there's not one cost fits all. Smaller systems reusing an existing furnace should be less than 10,000. Some future interests for me. That workshop I have, I didn't mention, has infloor tubing in the floor, but I did an experiment. You might have noticed that there were solar thermal panels on the wall of the workshop as well. And so I fed that heat into the floor, hoping that I could keep that workshop above zero during the winter time. It didn't work, but it was an experiment, so I still have that tubing. So I'd like to consider using the solar thermal in combination with an air-to-water heater pump to heat those tubes in the floor. Future replacement appliances, heat pump dryer. The nice thing about those is not only do you gain the efficiency of the heat pump in the dryer, but you also stop dumping what you heating the air inside the building through the dryer vent outside. While you're drying your clothes, you're removing the heat from your building as well. So the heat pump dryer does not have an external duct outside. I think the future will be those appliances we're now replacing will have smarts in them that can turn on based on solar or energy costs at the time. The future with electric vehicles, and you can link them to the home as well, so rather than adding dedicated batteries, you may be able to use your electric vehicle in the future to power your home. There are goals from the government and the Canadian Home Builders Association to put out standards for net zero renovations. So I'm interested in that and working with customers on projects along those lines. I'm hoping for simplified and cheaper battery installations moving forwards. A few recommendations for you. You did mention this. If you're going to get equipment, heating, ventilation, air conditioning equipment upgrades, always ask the contractor for a heat loss gain calculation to right size that equipment. If you're considering replacing your air conditioning, your cooling system, consider replacing it with a heat pump. Even if you don't use the heat pump initially, you will end up with a very efficient air conditioner, and then you have the ability to use it for heating when it becomes maybe more economically viable for you when the cost of natural gas goes up or electricity comes down, or it might make more sense. Look for experienced contractors. They'll usually be busy. I can testify to that. Ask for referrals to talk to their customers. If you're going to put in solar, I would recommend PV over solar thermal. There's no maintenance required and no limit to the feedback. You're not limited by the size of the storage tank. You can feed back to the grid as much as you want. One thing I didn't show a picture of, I have a domestic hot water recirculation pump, and that can save some costs on water that's running down the drain whilst you're waiting for hot water to get to the faucet. It's on a timer, so it only runs at certain times of the day. You can also have them be controlled by temperature as well, so they only run until the water in that line is hot. So you only have to run a small amount of water from the pipe directly below the sink to the faucet. And always, if you have a hydronic system, the lower the temperature you can get the building to be heated at, it will future-proof the system. So if you do replace the equipment from a natural gas boiler to a heat pump or to other renewable sources, it's a lot easier to do if you thought about the design initially that it was going to run at a lower temperature. Some useful resources for you if you want to Google some of the following. The Canadian Renewable Energy Association has a Go Solar Guide. There's lots of good information in there about if you're considering adding solar to your building. Natural Resources Canada has a resource called Keeping the Heat In. It's a really good document about renovating your home and how you can insulate and air seal, etc. The NRC also runs the NR Guide program, home evaluation. Really worthwhile getting an energy audit completed, and you can know where you're at and what's possible. City of Saskatoon has some great resources on their website. The solar heat map is the picture on the right here. Kind of gives you an idea of the potential of roofs. They have for their electricity and water customers a utility called Smart Util, which shows consumption. I think it's on 15-minute increments. They have the HELP program, which I used in my own home, which is a low-cost home energy loan, which allows you to buy and retrofit energy sure there's going to be a few questions.